All right, buckle up because today's deep dive is going to take us on a wild ride through the mind of Sir Roger Penrose.
Yeah, you've got quite the collection of Penrose's ideas here, from his talk with Kurt Mungle, his conversation with Lex Fridman, even dipping into Carlo Rovelli's work.
It's going to be a good one, so let's jump right in. Time, we all think we know what it is, this whole past, present, future thing, but Penrose, he isn't so sure it's that simple, is he?
Not at all. Rovelli, in his book The Order of Time, really breaks down this idea we have of time as something rigid and unchanging. He reminds us that Einstein kind of blew that whole concept out of the water with relativity. Time, as it turns out, is relative.
So what, like time flies when you're having fun? Is that what we're talking about here?
Well, kinda, but on a much grander scale. It's about how gravity and speed actually change the way time flows. Like, imagine you had a super accurate clock and you sent it out into space, away from Earth.
Okay, I'm with you so far.
That clock, out there in space, wouldn't match up perfectly with a clock here on Earth. Time wouldn't be moving at the exact same rate for both of them.
Whoa, are you telling me if I sent my watch into orbit when it got back, it wouldn't match the time on my phone? That's messing with my mind a bit.
And it gets even weirder. Think about this. Let's say you have a friend who decides to live on top of a mountain, and you're more of a beach bum.
I can relate to that.
Because gravity is weaker the farther you are from the Earth, your friend up on that mountain, they're actually aging a tiny bit faster than you are.
Hold on, you're telling me mountain air might not age you faster, but time literally moves faster up there.
Exactly. Time isn't this constant, rigid thing. It's more like, think of a river with currents and eddies. It flows differently depending on where you are in the universe, thanks to gravity.
So time is more like a river than I don't know, a metronome. Okay, that's wild.
And now, take that mind-blowing idea and stretch it out across the vast distances of space. Rovelli talks about this concept called a light cone, which basically says, because information can only travel as fast as light, what we see as happening now across the universe isn't actually happening all at the same time.
So, like what we see is happening right now on a star millions of light years away already happened a long, long time ago.
Exactly. Our concept of now is limited by how fast light can travel, which means our view of the universe is like, it's like looking at a photo album instead of watching a live video feed.
We're stuck with snapshots, not the whole movie.
Precisely. And what's even more, because of these light cones, what we perceive as simultaneous events in the universe might be happening at completely different times relative to each other. So if time can be so slippery, what about space? Is that up for debate too?
I'm almost afraid to ask, but yeah, let's dive into that.
Let's. Ravelli draws a really interesting comparison between Aristotle and Newton's views on space. Aristotle, he thought of space as how things were ordered, like the arrangement of objects. But then Newton comes along and says, nope, there's this thing called empty space where everything happens.
It's like the difference between thinking of a stage and thinking about what's actually going on in the play, right?
Exactly. And that idea of empty space was a big deal. But now, with quantum mechanics, we're starting to question if truly empty space even exists. It might actually be more like a bubbling quantum soup of particles constantly popping in and out of existence. Not empty at all, but bursting with potential.
Whoa. So it's less like an empty stage and more like, I don't know, a petri dish teeming with microscopic life.
A great way to put it. It just goes to show that reality is far stranger and more wonderful than it seems. And just as our understanding of space and time needed an overhaul, Penrose believes our approach to consciousness needs a serious upgrade too.
I mean, yes, he doesn't think we're just biological computers, does he?
You got it.
Mm.
In his conversation with Lex Fridman, Penrose really pushes back against this idea that consciousness is just a matter of computational power. Like if we build a big enough computer, boom, consciousness.
So it's not just about how many calculations a brain can do, but something more fundamental about the process itself.
Exactly. He uses Gödel's incompleteness theorem, which basically says even in math, there are true things you can't prove within a system. Penrose argues this means our minds can go beyond any algorithm. We can make intuitive leaps that go beyond pure computation.
Okay, now you've got me really intrigued. But how does that play out in the brain? Does Penrose give any concrete explanations for this non-computable consciousness?
This is where it gets wild. He proposes this model called orchestrated objective reduction, or ORCH, or R for short. And this is where things get really interesting.
Quantum mechanics and consciousness, we're going full-on matrix here. Yeah.
It might sound out there, but hear me out. At the heart of ORCH-R are these tiny structures in brain cells called microtubules. Penrose suggests that because of their unique structure, these microtubules can hold on to quantum states much longer than we thought possible.
Quantum states, like the same stuff that governs subatomic particles inside our brains.
You're getting it. And Penrose believes these quantum states are the key to how our brains go beyond simple computation. He thinks the collapse of these states in microtubules, what he calls objective reduction, could allow for those non-computable processes to happen. It's these quantum events that give rise to our understanding, awareness, all that we consider consciousness.
Hold on, so you're saying that at a subatomic level, our brains might be doing quantum computations? That's a lot to take in. I thought we were just talking about wonky clocks in space, and now I might have a quantum computer in my head.
It's a mind-bending idea, isn't it? And believe it or not, that's just the tip of the iceberg when it comes to Penrose. But before we go any further down that rabbit hole, I'm really curious. Where do you think Penrose takes us next? What about the other big question, even bigger than how consciousness works, the Big Bang itself?
So we've gone from questioning how time works to wondering if our brains might be tapping into the quantum realm. And Penrose, well, he doesn't stop there, does he? He sets his sights on an even bigger mystery, the Big Bang.
You're right. He doesn't just accept the Big Bang as the ultimate beginning. He's looking beyond that, asking what came before. It's a question a lot of physicists kind of shy away from, but not Penrose.
It is kind of like asking what's north of the North Pole, isn't it? But Penrose, he's not afraid to poke around in those cosmic corners.
And what's fascinating is it's not just philosophical curiosity driving him. He's bothered by this thing called the low entropy problem of the early universe. It's something that bothered him when other physicists didn't seem too concerned.
Okay, low entropy. That's one of those phrases that makes my brain do a backflip. Could you break that down for me? Maybe a metaphor or two, just to keep things from getting too tangled?
Sure. Imagine a box filled with 1,000,000 Lego bricks, all mixed up. That's high entropy. It's random, chaotic. Now shake that box. What are the chances those Legos would suddenly assemble themselves into a perfect model of, say, the Taj Mahal?
Pretty much zero, I'd say, unless you had some seriously lucky shaking going on.
Exactly. But that's the puzzle of the Big Bang's low entropy. It's like the universe started as a perfectly assembled Lego masterpiece, not a random jumble of pieces.
So instead of this massive explosion of chaos, the Big Bang was actually incredibly organized. That's a bit counterintuitive, isn't it?
It really is. Gravity, it loves to clump things together to create stars, galaxies, black holes. That's what it naturally wants to do. But the early universe, according to the standard Big Bang model, was super smooth and uniform, like a perfectly flat sheet of space-time. And that smoothness, that even distribution of energy, that's a surprisingly low state of entropy for gravity. It's like gravity started the race a few steps upon the starting line.
Like showing up to a marathon and finding out everyone else got a head start.
Exactly. It doesn't quite make sense. So how does Penrose address this?
Right.
Well, he doesn't just throw his hands up in the air and say the universe works in mysterious ways. He comes up with this mind-bending model called conformal cyclic cosmology, or CCC for short.
Okay, I'm gonna need you to unpack that one. Conformal, cyclic. It sounds like we're about to take a trip through a wormhole.
Think of it this way. Imagine a universe where black holes have basically swallowed up almost everything. That's where Penrose believes our universe is headed, eventually. Over unimaginable stretches of time, black holes gobble up matter and energy, even merging to become these supermassive giants. But even black holes aren't eternal. Thanks to Stephen Hawking, we know that they slowly evaporate, releasing what's called Hawking radiation.
Right, it's like they have a tiny leak, and over, well, a really, really long time, they eventually disappear.
Exactly. Now, here's where it gets interesting. Penrose realized that for things without mass, like the photons that make up light and Hawking radiation, time is fundamentally different. They don't age the same way we do. Imagine a photon traveling from a distant star to your eye. For us, it took millions of years. But for the photon, no time passed at all. It's like the universe is a flipbook, and photons can jump between the pages.
So a photon born at the beginning of the universe would experience the entire lifespan of the cosmos in an instant.
In a way, yes. Now, apply that to the very distant future, where black holes have evaporated and only these massless particles are left. Penrose realized that this incredibly vast, empty future would be, from the perspective of those particles, indistinguishable from the incredibly tiny, dense state of the very early universe.
Wait, are you saying the end of the universe could somehow morph back into the conditions of the Big Bang? Like the universe hits rewind?
That's the heart of Penrose's conformal cyclic cosmology. It's not a straight line from Big Bang to heat death, but a cycle, an eternal loop. One eon transitions smoothly into the next. No real beginning, no real end. The universe reborn from the ashes of its former self.
Okay, I'll admit it. That is one seriously mind-blowing concept. But hold on, if the universe keeps getting recycled, wouldn't each cycle be like hitting the reset button? And what happens to everything that came before? Does it just disappear? That is one seriously wild concept. But hold on, if the universe keeps getting recycled, wouldn't each cycle be like hitting the reset button? What happens to everything that came before? Does it just disappear?
That's where things get even more interesting. Penrose, he suggests that information, actual information, might survive the transition from one eon to the next.
Hold on, information can be passed from one universe to another, like some kind of cosmic inheritance? What kind of information are we talking about?
Not like messages in bottles or anything like that. More like think echoes or shadows.
Okay, I think I'm following.
Penrose, along with a physicist named Vahegirzadyan, they claim they found evidence of this information transfer. And get this, in the cosmic microwave background radiation.
Wait, the afterglow of the Big Bang? They're finding stuff from before the Big Bang in that?
That's the idea. They believe they've found these subtle patterns in the CMB that could be remnants of black hole collisions, but from a previous eon.
So we're talking about detecting, like, ghost signals, whispers from a universe that existed before our own. That's some serious cosmic archaeology.
Exactly. It's like finding fossils on a beach. But the fossils are from a time before the beach even existed. It challenges everything we thought we knew about how the universe works.
This whole idea of information surviving the death of a universe, well, it's incredible. Is that what Penrose is getting at with all of this? This potential for connection, for something beyond what we can even imagine?
I think so. If those patterns in the CMB are really what Penrose and Gurzadian think they are, it would completely change our understanding of the universe. It means our Big Bang wasn't a starting point, just a turning point in this endless cycle.
And if information can survive from one eon to the next, what else could be possible? It's almost too big to even think about.
Right. Penrose has even speculated, and this is where it gets really wild, that maybe, just maybe, the seeds of consciousness, those non-computable elements we were talking about, could be part of this information transfer too.
You're blowing my mind here. Are you saying that some part of our consciousness, our experiences, could somehow carry over from one eon to the next, like a cosmic reincarnation?
It's a bold idea, and Penrose is careful not to say it's definitely true. But if consciousness is truly non-computable, then maybe it plays by a different set of rules. It could exist outside of space and time as we understand them.
So, we're talking about a universe that not only cycles through time, but potentially carries with it the echoes of its past inhabitants. It's both beautiful and kind of terrifying to imagine. This deep dive has taken us from questioning the nature of time to contemplating a universe that remembers its past. Sir Roger Penrose, you've given us a lot to ponder. We've gone from the flexibility of time to the possibility that our brains might be these tiny quantum computers. And of course, we can't forget about those echoes of forever, the idea that information, and maybe even something more, could survive the death of a universe and be reborn in the next.
It really makes you want to just look up at the stars and think about, well, everything, doesn't it?
It really does. And for you listening, we leave you with this. If information can survive the death of a universe, what else might be possible? Is there an echo of ourselves, however faint, in the universe that came before our own? What will we, through our thoughts, actions, and experiences, contribute to the echo that remains when our own universe reaches its end? Until next time, keep those questions bubbling, and we'll see you on the next deep dive.